So you can see it's
one of the things that FTC teams are always trying to figure out is how can they pack more mechanisms into a smaller form factor for the robot.
Once all three balls are funneled into the triangle, we have this over-center linkage ramp, which pops down.
We're here at the World Championships with Team 22105 RunTime Terror for the FTC Decode season.
Why would you consider lifting your intake up?
And at FTC Robots Revealed, we get a up-and-close personal look at how all the different mechanisms function on robots so that your team can learn a little bit more about how to design things like this.
that we recommend to other teams if they want higher efficiency, and that allows our, and by reducing the amount of power transfers by having
This team's got a liftable intake, so they don't over-control the number of game elements. They've got an over-center linkage to be able to eject the artifacts out of the robot. Really interesting take on a spindexing design for their robot, and a power takeoff mechanism for their lifting.
So tell me about the overall strategy. What's your robot all about?
Yeah, so we are a far zone main robot, and we have a very unique design that we've coined funnel spindexer, #FDX. So essentially how our robot works is we want a full pass, we have like essentially a full pass-through design where balls can be intake 3 wide, right? And we can intake from clumps from the far zone, but at the same time, we also have sorting capabilities. So I'll go into a little bit more depth about how all that works. First, starting off with our intake. So our intake, everything is fully custom molded, and there's actually 4 sets of rollers here. There's 3 sets of silicone, all custom, and 1 of urethane. This first stage is just compliant wheels, and it drops down to prevent overpossession. Then the second stage, we have mechanisms that vector the ball to the center. That way, if one ball is here, another ball can go around. And then the third stage just makes it fully sit in.
Now,
This stage,
on your silicon wheels here, you actually don't have an insert on the inside of them, yeah? You just undersize that silicon insert? Yeah.
yeah. So,
Do you know what your durometer is on those wheels?
yeah, so all of these are 30A. And yeah.
Very cool. And
And
then
this
you...
one's urethane.
Okay. The one on the inside is urethane one. And then you super quickly went over, you said that the whole thing's able to lift up and down. You've got these little servos there. Why would you consider lifting your intake up?
It prevents overpossession. So essentially, once 3 balls are inside, wanted to demonstrate. Should hold this. Once 3 balls are inside, do we have a third ball?
No.
It's fine. But you can see with 2, like a third ball would sit under the intake, right? So if that happens, then you'll get called for a penalty, and that's not good. So this raising up and this also raising up essentially kicks out that third ball. So as soon as these 3 color sensors, which we have inside of our robot, detect that there's 3, instantly raises these up, and so we can just drive back and forth without having to let them like settle.
Once that intake brings it in, how do we actually get it into that? You were calling it a hashtag FSD, am I correct on that?
FDX.
FDS,
Funnel
sorry,
Spindexer.
wrong one. Okay. So what's going on there? What do we got?
yeah, sure.
Oh,
So you can see it's a really quick process. Or just want to about
Yeah, so basically, we specifically chose funnel spindexers so that most spindexers have like barriers or like recesses on the spindex, so they can't intake like 3 balls as quickly as we did.
Yep.
So we have no recesses, no barriers. It's 3 ball wide intake, almost as good as like just a normal pass-through bot. And then it all funnels into like this triangular formation. And then if you can like close up here, we have an over center.
Oh, over there. Okay.
Yeah.
You might have to get the
All the way on the
artifacts out of there, or it's too hard to see.
Got another
Thanks,
artifact. We can
Yeah, so basically, once all 3 balls are funneled into the triangle, we have this over-center linkage ramp, which pops down, and then the spindex spins, like here, and it transfers all 3 balls.
Okay, and it
you
just
can
runs right up that little ramp there. And it
Yeah.
looks like there's some grip tape. I think it's Cat Tongue
Yeah.
is a pretty
Yes.
standard American
That's
brand.
to
tune compression.
tune compression. And we also have this like blue feeder wheel over here that's it's like a 90-degree round belt all the way to the intake. And that helps it
yes,
come
I
up.
can see that round belt right in the back
Yeah.
left-hand corner of my current shot. Yeah, okay.
Yeah.
And that means that you have that that ramp back there is then also connected to here, here, and here. So
Yes.
you have 4 separate rollers all running on this intake.
It's also a feeder wheel right here.
Yeah.
Okay,
there's like
you
a-
got feeder wheel is
So it's
it's
this yellow
like
one.
on the
you got that
inside.
blue one, and you have a yellow one. Wow. Okay.
So this one is molded out of urethane actually,
Yeah.
and something about that one is something about the urethane roller is it helps us constrain all 3 balls.
Yep.
Not having recesses gives us a significant advantage when it comes to intaking quickly, but we've also had issues with constraining it. So we used to have a constraining pole over here to constrain all 3 balls when they were actually in formation, so that they would all shoot in a rapid fire location. But we realized that this compression roller was enough to constrain it and move it closer to the top while we were spinning it. So also, I guess as we talk about transfer, we can move into the shooter sequence. So we have a pretty standard counter roller shooter, but we've gone through quite a few iterations over these to optimize it to the fullest extent. So because we're a far zone main, due to the bot properties that Ethan will talk about soon, we wanted to have a bot that had a really low velocity drop over the course of 3 shots and had high efficiency while using decent RPM. So if you look over here, you see that we actually have a lot of, it's a little hard to see, but we have a lot of ceramic bearings everywhere.
Ceramic bearings.
Ceramic bearings, yeah. They're a little bit more expensive. We got them from Fast Eddie. They're a pretty good vendor. They allow us to optimize the slip, and it's good for high RPM efficiency. And we also use only 2 bearings actually connected to the main shaft. So we have this kind of shaft relief mechanism over here. So if you look at the main mechanism of the rack and pinion that connects these counter rollers, it's not actually connected to the shaft. It's independently mounted to this static plate on the inside, and it's a bigger bearing that goes around it.
Yeah.
This kind of mechanism basically allows us to not have the axial load of all of this onto the main shaft.
So essentially, to remove having extra bearings on this shaft, which will reduce efficiency, what we're doing is we have this larger bearing, which you can see right here, right? And it's just constrained on this plate, and it goes around this bearing while this just goes through the center of that large bearing and it just directly mounts here. So that removes any axial load from the main shaft of having all this stuff on that same shaft.
Because you have a whole whack
Yeah.
load of stuff that's sitting on top of that.
So yeah, how it works is a static kind of 3D print mounted to this plate, and then there's a bigger bearing that goes around. And then we have like this kind of moon disc that helps constrain that bearing.
Yep. Okay.
So
It's like, yeah, because that's quite a heavy flywheel.
yeah, so about the heavy flywheel, right? We probably use some of the most inertia, so 8,000 kilograms per centimeter squared, which allows us to have really high efficiency and low velocity drop over the course of 3 shots. And we're able to maintain that heavy load without any other things being inefficient because we're able to optimize efficiency on the main shaft. So as we go there, we have a pretty standard gear switch mechanism over here to switch the direction of the counter rollers in the back. And something unique we have is we actually, so next time about our guides, right? We've tuned a lot of different compression mechanisms for our guides, maybe like over the course of weeks, because we realized that in order to have the least amount of velocity drop, it depended on how the balls contacted the guides. So it's a little bit difficult to see here. If you remove this tape,
Yeah,
you can see that it's not actually a flat guide. It has this kind of crevice. And that means the ball is actually only ever contacting it on 2 edges and not actually completely on the flat surface, which reduces the surface area and reduces slip, which makes it way more efficient. So,
And then you use those counter rollers because you have the extra grip from that tape. You use the counter rollers to be able to affect that backspin so it doesn't launch itself out once it gets
Exactly,
to the
yeah.
gate.
that reduces our backspin
And
there.
also, essentially you get also with counter rollers, you get more energy actually going into the ball moving instead of the ball spinning. So like you could just like run it at less energy, less RPM, and get the same like length of shots.
And a few like last minute touches is just like here we only use 6 power transfers total, with 3 of these being, well now it's 2, but 2 of these being dead axle. And as you can see, we actually use 6mm D shafts and 6mm round belts. It's actually a lot better and more efficient at high RPMs than a lot of teams using 8mm Rex. So that's something that we recommend to other teams if they want higher efficiency. And that allows and by reducing the amount of power transfers by having 1 belt be connected and only a few here, it allows to have an efficient shooter with low velocity drop and make accurate shots. So Ethan, how about you talk about the rest of the drivetrain and how that integrated?
Yeah, so in terms of the drivetrain, we have a pretty unique setup in which we have the two motors are completely within the side panels of the robot. So we're running a parallel plate chassis like a very common parallel plate drivetrain, but the two motors are inside of the side panels. And we did this mainly because our robot was designed around our funnel Spindexer system. So that required the funnel Spindex to be incredibly low to the ground. So we didn't want to put any motors underneath it. That packaging the motors this way allowed for the motors to be moved from underneath the Spindex to the side panel. So that lowers the Spindex overall and allows for intaking to be a lot easier. And then in terms of transfer, we have a bevel gear system here. There's two bevel gears. That's geared to this axle. And then this axle drives the belt ratio, and then that drives the wheels. So we have a 383 RPM mechanism drivetrain.
So your output is 385.
Yes.
Gets out of the shaft.
And what this axle also allows us to do is, since we already have this live axle here, we have another pulley behind on the other side of this inner plate that acts as the PTO for our hang system, which Arush can talk about.
Yeah.
So,
and by hang system, you mean your lifting mechanism?
Yeah, no, we're still stuck in last year.
Yeah.
Yes, yes.
2 years of hangs in a row.
Yeah. So a little bit about the hang system is that initially we had a belly pan that pivots. Basically, we had it powered by 2 servos, and that was really inconsistent because we also had to curl. But now, what's special about this one is we have a full linear slide, Misumi slide hang. Mm-hmm. It goes a full 18 inches, and yeah, you can see here. You can see
That's
we have
held in by these small magnets.
Yeah, you can see magnets at the top.
And sorry, I did not see you catch the magnets on.
Here.
It's tough to do with your fingers. Okay.
Yeah.
So you've got a magnet on that side, and then the magnet is on the top over there.
Yeah.
Okay.
So we have the aluminum belly pan.
Mm-hmm.
You can see the mounts. We have carbon fiber mounts over here.
Mm-hmm.
And you can see what Ethan was talking about earlier, which is this drivetrain wheel. It belts up through this live axle through to this, and there's also an encoder on the other side to make sure it's all aligned for PTO later. And then this right here belts, as you can see, up through the back to up here.
Okay.
And I'll show that.
So once it's belted all the way to the back, we actually have a dog ear clutch PTO. If you go to the center here, you can see this small hole. Right at the center of that hole is, you can see the 2 metal.
So you've got this
beams.
one. This is on a servo, and there's a beam that comes out here.
Yeah, it's
and another beam that comes out there. Sorry, it's just hard to see, so I'm just following it.
Go on dash and change the position.
Yeah.
Mm-hmm. Mm-hmm. Okay,
And
cool.
if you zoom in here, you can once Serena does it, you can see the screw heads meshing.
And that
We have
is
to align with
way up here.
Do you know the
Yes.
position off the top of your head?
Yeah. So the reason we added encoders on the back too is because initially with no encoders, we had no way to tell how the screw heads were oriented, and it would actually mesh incorrectly, and it would desync and everything. So we added encoders so that the drivetrain doesn't move before we hang.
Something cool as well is originally we thought encoders wouldn't work because these spin continuously, right? So RPM wise, it just wouldn't work. But this actually has 4-fold symmetry. So you only need a quarter of the range, and so 360 absolute encoders actually work for that. So that was nice.
And then just for those that can't see, that's tough in here, you've got this belted plate here with some screws that are embedded on the inside of it. And then this pink plate shuffles over and it pushes that other little pink plate just in the inside there. And those 2 screws are what end up meshing, and you're actually driving using the screws to lift the whole thing up.
Yeah.
Yep.
And there's this large shaft that runs all the way across from here to here. That's normally not moving, right? Because this is just dead. This is just dead axled to it, right?
Yep.
But then that shaft, when this connects, becomes a live axle. And essentially also on that shaft through the middle, you can kind of see the bottom of it down here. We just have a ratchet. So just a regular ratcheting wrench that's 8mm because it's 8mm Rex. We just slid that on. that you can like click it back and forth, and that means that when our end game raises all the way up, we don't go back down.
You don't crash on top of the robot.
Yeah.
That's a bad idea.
Super slick. Super slick. And then what kind of things do you do on the software side to make your driver's life a little bit easier?
Well, first of all, in our far auto, if you on the front here, we have this camera, and we use ball CV in our far auto. So it scans the balls along the side of the wall and drives to it, which really helps us get those the output in auto much larger because you have way more consistent intakes. And we also use this camera for ramp CV, so we count how many balls are on the ramp, and then in our sorted auto, if we've missed a ball or something, it automatically, through a brute force algorithm, it checks what the best combination is, knowing how many balls are on the ramp, and shoots that instead of just the regular glyph. And we also have this in teleop. If we ever do teleop sorting, our driver 2 has those buttons that say like mod 2, mod 1, mod 0 for the number of balls on the ramp. Of course, we have our turret, our shooter, our hood. All of this is controlled automatically through linear interpolation, tuned data points. And our shooting, we have shooting on the move, which accounts for the robot velocity. And then we've also found that was kind of like when we were running in close zone, we would drive and then the turret would like lag behind because of shooting on the move because we're decelerating. So we also added acceleration compensation. So we account for the change of velocity and then use the change of velocity to calculate the new goal position. And then we also have one more camera on the back, which we use just for April tags and detecting the motif. In terms of controls, like there's one, I think we can demonstrate this if we start tally up. So if we intake 3 balls, you'll see it automatically goes into the transfer sequence. So we have 3 color sensors. You can see like one here, that's where the lights are coming from. Yep. And it automatically, it puts the ramp down, it rotates the Spindexer that degrees at the same time. So the first ball is in position to go up the ramp. And it puts this ball stopper, which I think Mechanical forgot to mention, up. We have this because we used to, if we didn't have this, and we would slam into a clump, the ball would start going up the shooter. So we added this ball stopper here to prevent the balls from going through the shooter too early. So we have that automatic transfer sequence where it just goes up, and so all the driver needs to do is hit the button to shoot.
Simple little door, and it makes it easy, right?
Yep.
Make it complex if it doesn't have to be.
Yep.
So what are you guys most proud about on this robot?
So I think like our robot's mission, our team's mission has been this season to not compromise on any part of the game. And I think we've done that and accomplished that as a team. So we have a hang, we have, a sorting system, but we don't have any bottlenecks and we're not limited in any way possible. And our goal from the start of the season was to win Worlds. We're at Worlds right now. Let's hope we can make the last part happen.
Very cool. Well, thank you for sharing, guys.